All right, let's look at something here. I'm going to draw you a graph, and you're going to tell me what function this is. So we have the axes there. If I have a curve going like this, what is this function? Is it a quadratic, linear, or what is it? Or is it something?
Exponential.
Yeah, it's exponential. So let's say this is anything exponential just means you have some base and then you just do to the power of 10. Oh, sorry, to the power of x. So here I'm going to say my base is 10 and I'm going to do to the power of x. I'm going to draw a line here. This is going to go through the origin. And it's also going to go through 1, 1, 2, 2, 3, 3, like that. What is the equation of this line that goes through the origin and goes through 1, 1, 2, 2, 3, 3? It's a straight line. That is y equals x, or 1x plus 0. The slope is 1 and the y-intercept is 0. Now what we're going to do is we're going to take this green line and we are going to reflect it on this dashed line. And it ends up looking like this. What is this function?
Rational.
So this one is y equals log of x. A rational function would be like that. It would have like two components because there would be a vertical asymptote. But this one is actually going through the x-axis. It's going to go through 1, 0 right there. So by itself, it just looks like this. This is called the log of x. It is the inverse. You can think of it, it's not the reciprocal, it's called the inverse of an exponential function. Now, inverse is something like sine and sine inverse, like these are inverse functions. Log of x is the inverse of an exponential function that has a base of 10. And you can get an inverse function by reflecting it on y equals to x line. So that's the idea. Inverse functions are something that you reflect on this middle line every single time. And come up with a bunch of other things as well. Let's say you have something like this, right? If you want to find the inverse of this, you reflect it on this line. It's going to be a little bit tricky to see, but it's going to end up looking like this. So inverse functions are something that you get by reflecting it on y equals to x line. That's one ways anyways, like there's other ways, but this is the graphical approach of an inverse function. And that's where the idea of log of x comes into play. Log of x is the inverse of 10 to the power of x. This is important. It's not 2 to the power of x. If you have 2 to the power of x, the inverse is going to be log base 2 of x. 3 to the power of x, it'll be log base 3 of x. But for 10, there's an invisible 10 here. We don't usually write that 10, just like how we don't need to write a 2 here. It's implied square root of 2. That means the index is 2. Log of x means the base is 10, okay? That's where it comes from. So to answer these questions, it's going to be a one-step answer basically for all of them. So it's asking us to write the inverse of an of this, right? So the inverse of this will be log base 3 of x. The inverse of this is log of x. The inverse of this is log 1 over 4x. And the inverse of this is what? For D.
Log mx.
Yeah, log of base mx. On the other hand, if you have a log function, that whatever this is, it becomes the base. So for the first one, you get 3 power x. What's D? What's the answer to D?
1/4x.
Yeah, 1/4 to the power of x. So that's the idea. Log is the inverse of an exponential function. We can also evaluate something like this. So this is going to be what we're going to be doing for the most part. And the idea is you need to be able to go from an exponential form to log form and vice versa. This is the idea. Let's say you have some a to the power of b, and let's say this is equals to some c, some value c. Right now, this is an exponential equation. We can turn it into a log equation by using this. This becomes log of base a and c over here, and this will be equals to b. So that's how you go back and forth between an exponential and a log. Here's a quick example. If you have 2 to the power of 3, we know that is 8. If you want to write it in this form, it's going to become log of 2, base 2, 8 over here, equals to 3. The base to the power of this will be this number here. Does that make sense? Let's try a few examples. What's the answer to A? So we're looking for a number, okay? 2 to the power of something is 4. And this is going to be the answer. 2 to the power of whatever this is will be 4. What's the answer?
2.
2. So log base 2 of 4 is going to be equals to 2. What's the answer to part B? 3 to the power of something is 27.
3.
3 is correct. What about C? 4 to the power of something, whatever. You can use a calculator. It's going to be 3. What about D? 5 to the power of something is 1.
It's 1.
5 to the power of 1 is not 1.
0.
0. E and F are slightly trickier, but 2 to the power of something is 1 over 2. It's a number less than 0. You can do it like this. 2 to the power of something, right? If I move this 2 in the denominator upstairs, what do I get? Right now it has a power 1 here, yeah?
Mm-hmm.
If you move it up, it's going to have a negative 1. It's going to switch signs if you move it to the denominator or the numerator. That's one of the exponential laws. Now look at this. Compare this side with this side. 2 is 2. That means what's the answer? What should this number be? Negative 1, right? Negative 1. So it's going to be negative 1. 2 to the power of negative 1 is 1 over 2. What's the answer to F? 3 to the power of something is square root of 3. You have to think of it in terms of exponents. 3 to the power of something is square root of 3. You can rewrite this in an exponential form. Square root of 3 means what's the power?
1 over 2.
Okay, so what's the answer to F?
It's 1 over 2.
It's 1 over 2, and there you go, you're done. So that's how you evaluate logarithms. Log stands for logarithms. That makes sense?
Mm-hmm.
It's this idea. You need to be able to go back and forth. So this to the power of something will be this number here. This is an interesting question. It says, why can't log base 3 of negative 9 be evaluated? So if you try to evaluate it, we're looking for 3 to the power of something, right? that's equals to -9. Is this doable? Is there any number that we can think of if we put it in here, we get a -9 on the right side? Here, I'll give you a sketch of 3 to the power of x. It's this guy here. 3 to the power of x. It goes through a y-intercept of 1, and it's going to go up the whole time. Is this graph ever going to cross the x-intercept? Think about exponential graphs. Do they cross the x-intercept? Can they touch? No, they cannot, right? There's actually an asymptote here on the x-axis for an exponential function. So what happens is this will just continue to ride the asymptote. It will never ever cross it. -9 is somewhere down here. The answer to this question is where this blue line and this red line meet, right? But the fact that the blue line never crosses the x-intercept means that they're never gonna meet. That is why this doesn't have a solution, okay? It's because there's an horizontal asymptote on exponential functions. I'm gonna skip this sketch for a bit. Yeah, that's super blurry. So this is our equation. And the goal is to solve for that t. That t is in the exponent, so it's gonna be a little bit different. How do we go about solving this? What would you do? Is it even solvable? There's two ways to do this. One of them is the dumb way, one of them is the quicker way. I'll show you both ways. Because they're both, I mean, they both work, so why not? One of them is this idea. 3 to the power of something equals 3 to the power of something. So over here we have t plus 1. If we can write 2187 in terms of 3, okay, in terms of 3, then this 3 and this 3 cancels out, and t plus 1 will be this number here. So for this one, I'm going to use my calculator. I'm going to do 3 power 8. I've overshot it. It's 3 power 7. So look at this. 3 power 7 is 2187 is equals to 3 to the power of t plus 1, right? Compare the left side with the right side. 3 is 3. That means what is t plus 1 equals to? So the base is equals to the base, yeah? That means the exponent should be equals to the exponent. So what is t plus 1 equals to in this case?
6 plus 1.
Yeah, exactly. 6 plus 1 or 7. And then you subtract 1 from both sides, t will be 6. So the answer is 6. That is one way of doing it. The other way is, because this way is not always going to work. Let's say instead of 2187, we had 2186. Now there's no way to write 2186 in terms of 3 power something. So this method is going to fail in that case. So what do you do in that case? So this is what you do. You've heard about squaring both sides, or, you know, whatever, adding 10 on both sides, or taking the inverse on both sides, sine inverse, like we did for trig. When we had like sine theta is equals to 0.3 or something, we took the sine inverse on both sides. That's why we ended up with theta is sine inverse of 0.3. Similar to that, what we're gonna do is we're gonna take the log on both sides. How does that work? So log of this right side is going to be equals to the log of the left side, like that. Why are we doing this? It's because log is very powerful. It has a special property. Well, it has a bunch of properties, but the most useful part about log is this. Log a, or let me just write, yeah, whatever. A to the power of b, log of a to the power of b. Notice how the b is in the exponent. If there's a log in the front, you can bring that exponent down. It's the exact same thing as b times log of a. An example would be if you have log of 3 power 2, that is the exact same thing as 2 times log of 3. You're allowed to bring the exponent down to the same level, okay? That's what we're going to do here. There's a log, that means this exponent, we're allowed to bring it in the front. So it becomes t plus 1 times log 3. And on the other side, we have log of 2187. Now here, we had an exponential equation in the beginning when the unknown was in the exponent. But now we have a linear equation. T is on the same level. How do we solve this equation for t? You want to get rid of everything that's not a t. So you want to get rid of the log 3, and you want to get rid of the plus 1. How do you get rid of the log 3?
You divide.
You divide. So log of 2187 divided by log 3 is equals to t plus 1. This you can put it in a calculator. It's going to be 7. So 7 is equals to t plus 1, and then subtract 1 from both sides, and you get t is equals to 6. So this is how you would solve it if you can't write this number in terms of 3 to the power something. And more often than not, you won't be able to write it. So this is the way to go. Does that make sense?
Mm-hmm.
So now we're back to this. We did a bunch of these, but these are slightly more trickier. 4 to the power of something is 64. What's the answer?
It's 3.
It's 3. That one's easy. 3 to the power of something is 1 over 27. Let's say that thing is x. 3, the answer to this, let's assume, is x. So 3 to the power of x is equals to 1 over 27. How do we solve this for x? Or what is the answer? If you see it, you see it. So that 27, right? Can we write that as 3 power something?
Yes.
So we have 1 over 3 cubed, right? Not 3x, 3
Mm-hmm.
cubed. Now if I move this 3 cubed here into the numerator, what does it become?
3 to the power of negative 3.
Exactly. So what's the answer to this question?
Negative 3.
Negative 3 is right. So 3 to the power of negative 3 is 1 over 27. The next one is very similar. So we have 2 to the power of x is equals to negative 4. Now think about the exponential graph, right? 2 to the power of x looks like this. Remember, there is going to be an horizontal asymptote on the x-axis. This is 2 to the power of x. Is it ever going to meet negative 4, which is down here somewhere?
No.
No, it's never going to cross that x-axis to be able to meet with this line. So what's the solution to C? How would you answer that? Like it's asking you to evaluate this, what would you write? Well, it doesn't have a solution, so you just write no solution. Don't leave it blank, yeah?
Mm-hmm.
That one is unsolvable. There is no solution. There is no solution on the real number system. What's the other type of number system we have? which we won't really get into, but there is a solution for this. It's not going to make much sense now, but there is a solution for this in the complex number system. Okay?
Mm-hmm.
Complex number system uses something called I, which is an imaginary number. I is equals to square root of -1. Using this idea, we can solve this equation in the complex number plane, but that is pretty advanced. We're not going to get into that right now. In the real number system, there is no solution. In fact, here, let me draw you a sketch of log of x. Doesn't matter what the base is, okay? Log of x looks like this. Doesn't matter what the base is. So let's say log base b of x. They all look like this. If the base is different, then it's going to increase slightly higher or slightly lower. Like that's the difference depending on what the base is. The exponential equation had a horizontal asymptote on on y equals to 0 on the x-axis. There's an asymptote on the x-axis. The fact that log is the inverse, right? Where would you expect the asymptote to be? So on the main function, on the exponential, there was an asymptote on the x-axis. On the inverse function, you'll have the asymptote on the y-axis, okay? Right here.
Mm-hmm.
Look at this sketch. What's the domain and range of this function then? Will it ever cross this y-axis? Remember, there's an
No,
asymptote there. So what's the minimum x value it can be? Can it be 0?
it can't.
It can't be. So domain is x has to be strictly greater than 0, cannot be 0. What about the range? Will look something like that. It just keeps going up and up. What do you think the range is?
Negative infinity to positive infinity.
Exactly. It can be any number. There's no restrictions on the range. So what this means is you cannot evaluate a negative number inside this. Okay, it doesn't matter what the base is, but inside you cannot have a negative number. Okay?
Mm-hmm.
Using this idea, tell me what's the domain. I mean, range is gonna be everything for everything. Let's say you have x minus 2. For this function, right, what will be the domain? What values can x take, in other words? Can x be 1?
No,
No. Can x be 2?
no,
Can x be 2.0001?
yes,
So what's the domain? X is bigger than some number.
2.
2, there you go. Domain, range is gonna be the same thing for every log function. So you cannot have a negative number inside here, okay? That's why this one, you can't evaluate it. Let's do D. So D is slightly trickier, but it's just 2 steps as well. So 5, let's say the answer to this is x. We don't know what that is, but 5 to the power of x is the cube root of 25. How do you go about solving this for x? Can we write the right side in terms of 5 to the power something?
Can you write 5 squared?
Yeah. Now think about that index. I want this to be in an exponential form, strictly as like 5 to the power something. So I can do exponent is exponent, base is base. Right now this cube root is hampering that, so How can we write this cube root as an exponent? Remember, it's the index. This thing, right, is gonna go down here.
Mm-hmm.
So 5 to the x is going to be 5 to the 2 over 3. The index always goes into the denominator in the exponential form. So what's the answer to this question?
2 over 3.
2 over 3, there we go. So the answer is 2 over 3. What did they say? There is no solution. Yeah, exactly. Don't leave anything blank. Sometimes they will try to trick you. So we're looking for some number. 5 to the power of some number is 47, right? You can just literally plug that in a calculator, but using logic, we can come up with like a decent approximation. 5 to the power of 2 is 25. 5 to the power of 3 is 125. So what possible numbers could this box take? It can take a range of numbers. What could it possibly be? If 5 power 2 is 25 and 5 power 3 is 125. This number in here must be between 2 to 3, right?
Mm-hmm.
It's a number between 2 to 3. Is it going to be closer to 2 or is it going to be closer to 3?
To 2.
To 2, right? So can't be 2.5 because 2.5 is equally spaced away from both of these. So the answer to this, again, is asking us for an approximate. I would say it's going to be 2.25. It's a number between 2 to 3, but that number is closer to 2 than it is to 3. So 2.25. Kind of make sense?
Mm-hmm.
Let's check what the actual answer is. 2.39 was the actual answer, but they use the graphing calculator. You can plug it in a calculator, but sometimes you can't. By that, I mean sometimes your tests will not allow you to use a calculator, and then what do you do? That happens for SATs. If you're planning on taking SATs, probably not. I don't know. Do you want to go to university in the US?
No.
Because if you do, you need to take these tests. And I know for a fact, one of the math tests that you do, you cannot use a calculator. And that question could come up on that test. Let's look into these. Log of 6 to 1. What's the answer to this? This one's pretty straightforward. 6 to the power of something is 1.
It's 0.
0 is correct. Now B is a little bit different. What's the answer to B? It has something to do with this fact. Yeah, it's exactly X. Because of this property. You have some function f. You combine this with some function that's the exact inverse. They cancel each other out. Doesn't matter the order. You can have the inverse first and then f later. They cancel each other out. So log of base 5, right? Log base 5 of x is the inverse of 5 to the power of x. So this log 5 and this 5, they cancel each other out. The answer is x. What's the answer to C? It's the same kind of idea. Just the order is flipped. Six to the power of x and log base 6 of x. How are they related? Same idea as before. They are inverses of each other, right? 6 to the power of x and log base 6 of x are inverses. So this 6 and this log base 6 are going to cancel each other out. And the answer will simply be an x.
Okay.
So most of these are going to be one-step answers. What's the answer to A? It has something to do with the fact that 3 and log base 3 and 3 to the power are inverses of each other.
It's 5.
It's 5. What's the answer to B?
Is it 2?
For B, it's 25. Here, let me show you. So we have 5. Again, this is the easiest way, right? They just cancel each other out because they are inverses. If we have 5 log 5 of 25, right? Forget about this 5 for a second. Let's just focus on the exponent. Log base 5 of 25. What's the answer to this? 5 to the power of something is 25. What's that something?
2?
2, right? So this entire exponent is actually 2. So you have 5 power 2, you have 25. That makes sense?
Mm-hmm.
That's one way. Another way is that this and this are inverses, so the answer has to be 25. C is the exact same thing. What's the answer to C?
1/16.
Yeah. What's the answer to D?
N.
E?
B.
What about the last one, F?
0.
Yep. One and done. Here's a biology application question. You're looking at mold spores in a petri dish. So initially there are 40 and it's growing at a rate of 10 times 10 every week. And the question is, how long will it take for there to be 2,000 spores? I'm gonna have to use an exponential formula for this one, which says the final count of whatever it is, it's going to be the initial number times the growth rate to the power of time. So in this case, what's our final count? It's one of those 3 numbers.
It's 2,000.
Our initial count is 40. What's our growth factor?
10.
10 to the power of t, like that. Now we have an exponential equation. How do we solve this for t?
You divide by 40.
That's right. So this 0 and this 0 cancels out. 200 over 4 is 50 equals 10 power t. Now what?
You do log.
Yes. So it becomes log of 50 is equals to log of 10 power t. What's the next step? So this t, right? There's a log in front. What can we do with that?
It goes to the front.
Yep. So you get log of 50 is equals to t times log of 10. Now what do you do to solve for t? You divide both sides by log 10.
Mhm.
Final answer is going to be log 50 over log 10, okay? And that's not 5. This you can't just be like log and log cancels out and 10 goes into 55 times. No, you cannot do that. This number here is probably going to be, what, 1 point something. Or actually, I don't know. Let's check. Probably not 1 point something. So log of 50 is definitely not 5. That was the point. Divided by log of 10 is, yeah, it's 1.69. So after 1.69 weeks, your mole spore count would reach 2,000. Have you seen like spores on a petri dish in class?
No.
Okay, maybe you'll do this later down the road, but they are a pain to count. Counting them is very like annoying because there's so many of them, right? Well, and
Mhm.
you have to be very careful. I mean, at the school level, it doesn't matter, but like if you work with them or something, then it's super difficult to get a precise count. It's a very tedious and slow process. I'm not a big fan of counting spores. Let's go to question 12. Have you heard of the term half-life? What is half-life?
Mhm.
We have briefly talked about it. So the last one was like a biology question. This one is like a physics question, all of which has applications in maths. So half-life is that it says right there, it's the time it takes for something to lose half of its mass. And usually it's going to be for something that's radioactive. Let's say you have plutonium or something that's radioactive. What happens is that the radiation it gives off, right? Like these things, it contains some of the mass of the substance itself. So what happens over time is that let's say you start off with 100 grams. Eventually, this thing will become 50 grams. And the time it took for it to go from 100 grams to 50 grams is called the half-life. Let's say, for our sake, this took 30, or I don't know, let's pick a nice number, 200 days. So it took 200 days for it to go from 100 grams to 50 grams. So 200 days, it's going to be its half-life. 200 days later, what's going to be the new mass?
0.
Not 0. It's going to become half. It's not linear. What's half of 50?
25.
25, exactly. So it's gonna be it's exponential, it's not linear. If it was linear, it would be 0. And then again, 200 days later, what is it gonna become?
12.5.
Exactly. So half-life is the time it takes for a radioactive substance to lose half of its mass. And we use this quite a bit actually in carbon dating, geology. If you want to find how old, like, I don't know, dinosaur bones are or something, we use this technique. So let's look at this question. We're given an equation. It's a complicated looking equation. It's not that bad. Like MT is the final mass, right? This is the final mass. P is the initial mass, just like we did before. And the growth factor here will always be 1/2. Last time it was 10 because it was increasing the mole spores, but half-life, it's always going to be 1/2, how long it takes for it to lose half of its mass. But last time in the exponent, we had T, but now we have T divided by H. T is the time that has passed, just like the T for the last question. And H is the substance's half-life. How long does it take for it to lose half of its mass? So that is the equation. Let's look at question A. If a lab has 5 grams of radium, which one of these variables is 5? P or MT?
P.
P is 5. 1/2 is always going to be 1/2. How much will there be in 150 years? So what's our T value?
150.
150. Do we have H? We do. It's 1620. So 150 divided by 1620. And you just plug this in a calculator. Are we expecting the number to go up or down, the mass, after 150 years?
Down.
Down. 50 divided by 1620. So this is going to be 4.68 grams. That's the answer to part A. Part B, it says, how many years will it take until the lab has only 4 grams of radium? Now what have they given us? What's 4?
M of T.
Yeah, M of T, the final value is 4. P was given before, it was 5 grams. 1/2 is 1/2. What's missing? What are we looking for when it says how many years?
T.
T is missing, and our H is still 1620. How do we solve this equation for T? You want to get rid of everything else that's not a T. So let's first get rid of that 5. What do we do on both sides?
You divide by 5.
So that's going to be 0.8 equals 1/2 to the power of T over 1620. Now what do we do? We need to bring the T down. And you can only bring it down on this step. In the previous step, you couldn't have because there was a 5 in the front. But now you can. How do we bring the T over 1620 down?
You do log.
You'll do logs on both sides. So log on the left, log on the right. And then that gives us log of 0.8 is equals to T divided by 1620 times log of 1/2. Now what? You want to get rid of that 1620 as well as log of 1/2.
You divide by log over 1/2.
Right, so it'll be log of 0.8 divided by log of 1/2. That is equals to T over 1620. What's the final step?
You multiply by 1620.
And you're pretty much done. So it'll be log of 0.8 divided by log of 0.5 times 1620. And the time is 521 years. So that's a long time. What if I asked you, its initial mass is 5 grams. How long does it take for it to decay to 2.5 grams? What would be the answer? You don't have to do any maths for this. The answer is one of the numbers in the question. We had 5 grams. How
It's
long
the
does
half-life.
is the half-life? 1620, right? So this answer here would be 1620. What about to become 1.25 grams? If we start off with 5 grams, how long does it take to become 1.25 grams? So you need to go through 2 cycles of halving.
It's another 1620 years.
Yeah, so it'll be what, 32, 40 years, right? Like that. There you go. So for this one, you don't really have to do maths. Here's an astronomy question. So that's our equation. D is the time it takes for a planet to revolve around the sun. And K is the distance from the sun in millions of kilometers. This thing here, 150 million, is this D or K? Or neither? It has something to do with the K, right? K needs to be in millions of years. So if they give us 150 million, what do we put in here as K? Log of what? How many millions in 150 million?
150.
150 minus 0.7. So 1.5 times log of 150 minus 0.7. That gives me 2.56 days. And that doesn't make any sense. The answer to this should have been 365. Let me try plugging in log of 150 million. Because I think that was the issue. But it does say K has to be in millions, so I don't know why. 1.5 times log of 150,000,000 minus 0.7. There is something wrong. That is also not giving me a nice number here. What is going on? I don't know. There's 150 millions in 150 million, so I don't know about this. But the answer to this, I think, how long does it take for Earth to revolve around the sun? Like we're doing like one full orbit. What is this thing called? It's a year, right?
Mm-hmm.
That's what we define as a year. How long does it take to do one full orbit? Yeah, the answer to this should have been 365. So I don't know what is going on. This number is right, I think. I don't know if this equation is right. Let me just look this up. Kepler equation for days revolve sun. I can't really find any equation. Whatever. That's the way to do it. I don't know if this 150 million is right. The answer to that should have been definitely 365. Let's look at another biology question. By the way, things such as mold spores and bacteria such as E. coli, have you heard of this? You can get this in your food, makes you sick, makes your tummy growly. These are used extensively. The question is why? Why are we using mold spores and bacteria? They have a very unique characteristic. It has something to do with this sentence right here. Is because they grow very fast, yeah?
Mm-hmm.
If you do it on rats or something, by the time one generation of rats have reproduced, you'll have thousands of generations of E. coli. So you can basically get an idea of what will happen in the future much quicker using things such as these, okay?
Uh-huh.
That's why we use like these small things. Human trials are like at the end. That's at the very end, and it needs a lot of approval. These things, you can go ham with them from the beginning. So it has a doubling period of 0.32 hours. This is our equation. Y I am assuming is the final count. Y0 is the initial count. T is the time that has passed, and D is the doubling time. So in this case, it's going to be T over 0.32. And there were 100 bacteria to begin with. So which one of these values is 100? Y or Y0?
y0.
Yeah, y0 is 100. So we have 100 times 2 to the power of t over 0.32. We can graph this. We would need a table of values. I'm gonna do the questions D to E, I guess, these two. I don't feel like using a table of values right now. So this is our equation. The goal is to come up with an equation for the inverse. I'm going to give you a quick example using a linear function, and then we're going to come up with the inverse of this function. Let's say you have y is equals to 3x plus 9. The question is, what is y inverse? What is the inverse of this function? What you do is you do something called interchanging. You can do this graphically, but it says come up with an equation, so we have to do this algebraically. We're going to interchange x and y. That's the first step. And after you're done with this, you're going to solve for the new y. What does this even mean? So x becomes y and y becomes x. Look at this. So y will become x and x will become y. And then now we have to solve for this new y. How do we go about solving for y here?
You subtract 9.
Yeah, you subtract 9 and you divide by 3, right? And you see this? This is your y inverse. That's the idea. We're going to do the same thing with this equation. We are going to interchange x and y, or in this case y and t, and then solve for the new y. So this becomes t is equals to 100 times 2 to the power of y divided by 0.32. How do we solve this equation for y?
You divide by 100.
That's correct. So what's the next step after dividing by 100?
You do log.
You do log. So you have log of t over 100, right? Is equals to, again, if you do log, you can bring that guy in the front. It'll be y over 0.32 times log of 2. What's next?
You divide by log of 2.
And then you multiply it by 0.32 and you're done. Times 0.32, and this is going to be your y inverse. So this, our main equation here, this gives us count, whatever this E. coli count, their numbers, when we are given t, given the time or whatever it is in this case. It's in hours, yeah, so time in hours. What do you think the inverse gives us? What does this equation give us? It'll be the opposite. This equation will give us the time, okay? It will give us the time. Y inverse in this case is the time. It's the opposite when we're given the count, okay? Look at part E. It says how many hours will it take for there to be 450 bacteria? Which equation do we use?
The inverse one.
Yeah, exactly. This is our time here. So we're gonna plug 450 as t over here. So let me plug that. So it'll be log of 450 divided by 100 divided by log of 2 times 0.32, and that gives me 0.69 hours. Now let's see if that makes sense. So initially we had 100, okay? after 0.32 hours, how many are we gonna have? It doubles, right? So we will have 200.
200.
After 0.32 more hours, how many are we gonna have?
400.
400, right? The question was asking us for 450, which is very close to 400. So far 0.64 hours have passed, and our answer is 0.69. So it makes sense that 450 would be at 0.69. And that's the answer to this question. All right, let's call it there.
Okay, thank you.
See ya.